Hey there, in this video I want to run through some linear algebra operations you can do with Python. Python's really quite powerful when it comes to doing matrix operations like finding determinants, inverting matrices, multiplying matrices. We've already seen the solve function. So to start out with, let's type out some arrays, some matrices that we can use here. We'll start with V being a vector, and we'll just hard code that to 1, 2, 2, and let's make two square matrices A and B. We'll just make them 2 by 2 so we can check the numbers by hand if we want to make sure everything's just like we'd expect. So np.array here, we'll do 2, 3, 4, 5. 2, 3, 4, and 5. And I'm typing these as floats just so I can be guaranteed that the mathematical results I get out are going to be floats as well. Remember, NumPy arrays have a type. So while I could get away with using integers for most of what I'm going to show you, I just want to be completely sure we don't have any weird rounding to the nearest integer going on. Anyway, for array B, let's go with 1, 1, 0, 1. Okay, let's just make sure that cell runs. Good. So we've got our arrays. We have a column vector, and then we have two arrays. First thing I want to show you is finding the magnitude of a vector. In Python, that's called norm. And linalg here is SciPy's version. I'm using scipy.linalg. So linalg.norm, and let's give it v. You can see that has a magnitude of 3, and you could check for yourself that 1 squared plus 2 squared plus 2 squared square rooted is sure enough 3. Let's look at the identity matrix. So let's say I want to make an identity matrix. That would be a matrix that's 1 along the primary diagonal. I can do that out of NumPy with something called identity. This is going to make an array that's 1s down the diagonal. And identity matrices have to be square, so we have to give it one value here. This would make it a 3 by 3. So it gives me a 3 by 3 identity matrix. Let's say I want a 20 by 20 identity matrix. Well, that doesn't quite fit when I'm zoomed in this much. How will we go 10 by 10? There you go. You can see we have these 1s down the diagonal. So just a nice quick way to make an array like that. Sure, you could build one using something like a for loop, but why not when you have a built-in function? Just use that. Let's look at finding a determinant. So here's array A that we're going to use. Let's find the determinant of that. It's a small enough matrix that you can do this by hand, but hey, why don't we just make the computer do it? So we'll do determinant of A and find that the determinant looks like it's -2. We've got floating point numbers here, so values aren't always going to be exact. -2 can be exact in your computer, but values here like, well, when you start doing the determinant, you end up with some rounding error from your floating point values. So that should be expected. You're never going to get something exact with floating point numbers. We can do the transpose of matrices. Now we just do a .t here, and it's not a function, it's just an attribute called .t. In fact, any NumPy array has this. This is just something that arrays have. So if you ask for that attribute, it's going to return the transpose of the array. Now if you're feeling like, oh boy, this is really wasteful, every array is stored in memory twice, that's not actually the case. The array is only stored in memory once. This is just called a different view of the array. It takes the very same data and just shows it to you differently. So there's no real efficiency loss by having this. Next, let's look at matrix multiplication. So you might think we could do A times B, but that doesn't quite work. What that does is it multiplies element by element. So we had 1, 1, 0, 1. We're just multiplying. So 2 times 1 is 2, 3 times 1 is 3, 4 times 0 is 0, and so on. That wasn't what we want when we multiply matrices. So we need a different operator here. And it turns out Python does have a matrix multiplication operator. It's the @ sign. It only works with NumPy. So what happened is NumPy defined this operator, but then didn't assign anything to it. It just says, hey, this is an operator that's out there if anyone who's writing a library wants to use it. And so NumPy uses it here for the matrix multiplication. But if these are NumPy objects, and they're NumPy arrays, they will know how to @ each other, or they'll know how to multiply each other. In doing that, we get the matrix multiplication result of A and B. So if I try to just matrix multiply like 1 and 2, it says ints don't know how to matrix multiply, and so I'd get an error. Okay, so all that's great. We also have the way to get inverse matrices. So if I want to get the inverse of A, I can get that from linalg.inverse A. Okay, that's the inverse. And we can check, hey, is that really the inverse? So we could take the inverse and multiply it by the original, and that should give us the identity matrix. When I say multiply, I mean matrix multiply. So we can check, is that the identity matrix? Yeah, at least within rounding error, it should be the identity matrix. So we've already seen solving. Now I want to show you something else here that has to do with the possibility of rounding error, and I've brought up rounding error a few times so far in this video. So let's create some matrices. First, let's start with an example that works, and then we're going to make a very tiny change to it, and it's going to make it break. And we want to look at how it breaks and how we can detect that things are untrustworthy. So I'm going to start here. We're going to make this a 3 by 3. And matrix A will be 1, 2, 3, 4, 5, 6. You can see I thought a long time about what values I wanted to use here. 7, 8, 10. Okay, tricked you there. So that's our A, and then our V is our column vector. We will make that equal to the very first column, 1, 4, 7. And I'm doing that on purpose because that makes this equation trivial to solve. If you think about it, what it means is if we have, these representing the equations 1x plus 2y plus 3z equals 1, and then so on, that means that once we write down the system of equations, x has to be 1, and y and z would have to be 0. So I already know the solution to this one. Nonetheless, let's look at what we get if I do a linalg.solve of it. A and V. And again, I'm expecting the answer to be 1, 0, 0. And in this case, the answer is 1, 0, 0. I mean, at least out to 16 decimal places. We do have a little bit of rounding. Okay, so let's take that and we're going to make one little change. You may have wondered, why didn't I just do 7, 8, 9? Okay, so let's try 7, 8, 9. Such a tiny change. And we still have V matching the first column here. So the solution still needs to be 1, 0, 0. And now we might notice here a warning message in pink. Result may not be accurate, right? And when we see these pink warning messages, our response shouldn't be, oh, ignore it. Right? Maybe we should actually look at it. And let's look at what our answer was. Yeah, that is definitely not 1, 0, 0. These values are very different than what the answer actually should be. What's going on? Well, in the course of solving an equation, I mean, we've talked about how to use Gaussian elimination, but from a pure mathematical point of view, what you're really doing is inverting A and move it to the other side of the equation. That lets you solve for X. And if we look at the inverse of A, again, this is A right now. 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks pretty innocent. Its inverse is absolutely gigantic. These values are huge. And what's going on with that? Well, if we look at the determinant of A, is 0, or it's 0 within rounding error. It's actually rounding to a little bit off 0. And that's called a singular matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9 is a singular matrix, which means you can't invert it, which means you can't really use it to solve the equation. All right, so that's what has happened here. And if it was exactly singular, you'd expect the program to crash because you'd have a 0 determinant. But the thing is, like, these values round a little bit, and so it's slightly not singular, but it's close to singular, and so you get this broken behavior. Well, let's make it so it's not singular. So let's add a little bit here. So we'll make this 1.001 up here. Okay, and that should change it. This is no longer technically singular anymore, and computers have lots of decimal places, so this should work. It won't be exactly 1, 0, 0, but it should be really close to 1, 0, 0. And it's not. Why? Well, it's still close enough to being singular that we are having trouble when we try to calculate it in our computer. So now what do we do? How do we detect that this is going to happen? Because wouldn't it be terrible if you wrote a program that depended on solving a matrix equation and it just outright gives you entirely wrong values? In fact, in this case, it didn't even show us the pink warning message, but it still did a really terrible job of returning the values for us. What kind of warning did we have? Well, there is something called a conditional number that you can calculate for a matrix. And if we get a large result that tells us that our matrix is poorly conditioned, we'd call it. And roughly speaking, the conditional number that we calculate here is a multiplier to the error. So if we get a large conditional number, we know, uh-oh, there's something wrong. And your computer can check for that. Now, unfortunately, we don't have one in the SciPy. So if we try to type out conditional, it's just not there. This is one place where we need to use NumPy's version of Linnell, like the only one, the only place. And here we do have something called conditional, and if we look at it, it returns the conditional number. So if I ask for the conditional number of a, here's our current value of a up here, we get a very large number. And so that means that that's a poorly conditioned matrix. It is close enough to being singular that we're going to get a lot of rounding error when we try to use it with floating point numbers. So at the end of the day, if you are blindly solving matrix equations without knowing that they are well conditioned, you should check the conditional number before you believe the result you're getting. Otherwise, you can get really wacky results where the computer happily gives you a number, but it's not really that meaningful.